In this lecture, we will look at the second category of reactions of aryl halides, which are the electrophilic substitution reactions. Electrophilic substitution reactions of aryl halides. Right, to begin with, let me tell you what is an electrophile. Electrophile means electron loving or electron seeking. So these are the groups or atoms or species which seek for electrons. Now why do they seek for electrons? Is because they are themselves electron deficient. So these are electron deficient species and hence they love electrons. Hence they are called as electrophiles. Now for example, any positively charged species like a Cl plus or NO2 plus or a CH3 plus, any positively charged species is an electrophile, because being positively charged, it will always have a tendency to gain electrons, right? So positively charged species, sometimes species like BF3 and AlCl3 are also electrophiles, and this is because in both the cases the central atom has got only 6 electrons around it, and therefore the octet is incomplete. So with incomplete octet, such molecules, such species also can act as electrophiles. So benzene and the aromatic hydrocarbons, they undergo electrophilic substitution reactions very easily. Why? See, benzene is a storehouse of 6 pi electrons. So it is electron rich. And if it is electron rich, certainly electrophiles will have a tendency to come and attack, because they are electron rich. And what are electrophiles? Electrophiles are electron deficient. So benzene and its derivatives, they undergo electrophilic substitution reactions very easily. Now we will try to draw a comparison between benzene and chlorobenzene. Now, when we compare benzene and chlorobenzene with regard to electrophilic substitution reactions, it is found that what is observed is that benzene is more reactive. Benzene is more reactive than chlorobenzene towards electrophilic substitution. Now what is the reason? Why is benzene more reactive, or why is the chlorobenzene or the haloarenes, they are less reactive? To understand it, we will have to consider the minus I effect of the halogen. The halogen atom attached on the benzene ring is a deactivating group. It is a deactivating group. Why? Because it shows minus I or minus inductive effect. And what happens because of the minus I or the minus inductive? The halogen tend to withdraw electrons towards itself. Being minus I, it will withdraw electrons towards itself. And now when the halogen will withdraw electrons towards itself, what happens to electron density in the ring? The electron density inside the ring decreases. Okay, the electron density inside the ring decreases, or you can say the ring is slightly deactivated. The ring gets slightly deactivated because electrophiles are in search of electrons. And now if you compare, where will the electrophile get more electrons? Will it get more electrons in the benzene ring, in just benzene, or in the chlorobenzene? Because of the minus I, some of the electrons are withdrawn by the halogen atom, and therefore the electron density in the ring decreases. Therefore its reactivity towards electrophiles will be less. So we have concluded that haloarenes are less reactive. They are less reactive than benzene towards electrophiles. I am representing electrophiles as E plus towards electrophiles due to what? Due to their deactivating nature. Okay, due to their deactivating nature. But they still undergo, okay, they are less reactive, but they do undergo electrophilic substitution reactions, right? And now we have to consider one more thing. When they undergo electrophilic substitution reactions, they are the haloarenes. The haloarenes are ortho and para directing towards electrophiles, which means the haloarene is going to direct the incoming electrophiles to which positions? Ortho and para. And what is the reason behind this? The reason behind this is resonance, plus R, or the plus mesomeric effect. See, if you consider the resonating structures of chlorobenzene, which we have seen earlier also, it shows plus resonance, and electrons are moved towards the ring and shifts towards the ortho position. So I am writing the same 5 resonating structures of chlorobenzene: chlorine positive charge, ortho negative, and then these electrons coming here and these moving to the para position. The next structure where the para is negative, and again a shift in electrons makes the ortho position negatively charged, and finally we get the same structure. So we have seen these structures earlier also, and what we see is that in all these structures, the ortho and the para positions, they specially take up what charge? Negative. Okay, so because of resonance, the ortho and the para positions in chlorobenzene take up what charge? They take up negative charge. Now just imagine an electrophile which is E plus or electron deficient. So electrophile is in search of electrons. Where will it get more electrons in chlorobenzene? Certainly it will be getting more electrons at the ortho and the para positions. So where will the electrophile go? The electrophile go where it will get a negative charge, and the negative charge is where? At the ortho and para position. Therefore, haloarenes are ortho and para directing towards electrophiles. So remember two things. Halogens, remember these two important things, that a halogen atom shows minus I, but it shows plus resonance. Because of minus I, it becomes a little less reactive. Okay, so minus I is controlling the reactivity. Minus I is controlling the reactivity, making it less reactive. But because of plus R, they are still ortho and para directing. Okay, and this is the orientation where the incoming electrophile will go. That orientation is decided by the plus resonance effect. So they have minus I but plus R. Because of minus I, they are less reactive, but because of plus R, they are still ortho and para directing in nature. Now let's look at the various electrophilic substitution reactions that chlorobenzene undergoes. The first reaction is halogenation. Okay, in halogenation, chlorobenzene is made to react with some halogen, like let's take chlorine, in the presence of anhydrous FeCl3, which is the catalyst, right? So it's halogenation. So what is substituted on the ring is a halogen atom. And where will it be? Remember the directive influence. The halogen atom is ortho and para directing. So the incoming electrophile, which is Cl, moves to ortho position and it moves to the para position. So you will get two products. One is ortho substituted and one is di substituted. One is para substituted. The para substituted product, this is the ortho and this is the para. The para product is the major. Why? Because para is symmetrical, and being symmetrical, it is more stable. and hence the para product is the major product. So this is first electrophilic substitution reaction. What is that called as? Halogenation. Let's take up the second reaction, which is nitration. Now in nitration, chlorobenzene is made to react with a mixture of concentrated nitric acid and concentrated sulfuric acid. A mixture of concentrated nitric acid and sulfuric acid. This is known as the nitrating mixture. Okay, it is called the nitrating mixture. So chlorobenzene is made to react with nitrating mixture, and exactly same thing happens. We get two products. In one, the electrophile comes at the ortho position. In the second, it comes at the para position. And what is the electrophile in nitration? It is NO2. So nitro group substitutes at ortho and para. Once again, the para product being the major product. So this is nitration of chlorobenzene. Moving on to the third reaction, which is sulfonation. In sulfonation, chlorobenzene is treated with concentrated sulfuric acid. The only reagent required is concentrated sulfuric acid, and it is heated. And similar thing, that we get two products, one ortho substituted and number two para substituted, and the group, the electrophile is SO3H, that is the sulfonic acid group. And once again, the para product is the major. I'll write the name of this compound for you. Sulfonic acid is a group of higher priority. So this is 1, 2, 3 and 4. So this is called 4-chloro. This is 4-chlorobenzene sulfonic acid. The major product is 4-chlorobenzene sulfonic acid. Now the fourth reaction in the category of electrophilic substitution is a name reaction. It is called the Friedel-Crafts alkylation. Friedel-Crafts alkylation. This is going to substitute an alkyl group on the ring. So we take chlorobenzene and we make it react with an alkyl halide like CH3Cl, whichever alkyl group you want. Like if you want methyl, so take methyl with the halogen atom. Alkyl halide in the presence of same catalyst anhydrous AlCl3. So which group gets substituted? It is alkylation. So which group will be substituted is the alkyl group. Where will it be substituted? One ortho and one para. So which is the alkyl group here? Methyl. So we will have one methyl at ortho and one methyl at para. Certainly para is the major product, and if you name this compound is 1-chloro 4-methyl benzene. 1-chloro, this is 1, this is 4. I am numbering alphabetically. C comes first. So 1-chloro 4-methyl benzene is the IUPAC name of the major product here. The last and the fifth reaction is Friedel-Crafts acylation. This is Friedel-Crafts acylation, and this is going to substitute an acyl group. Acyl is what? It's an RCO. Acyl group is a RC double bond O. So for this, with chlorobenzene, I will take an acid halide RCOCl. Okay, in the presence of a catalyst anhydrous AlCl3. These compounds are called acid chlorides. This one is particularly, if you name it, this is ethanoyl chloride. What is the name of this compound? It's ethanoyl chloride. Okay. And which group will be substituted? Acyl. Where is the acyl group? RCO. This is the acyl group, RCO. So this group will come on the ring, right? And where will it come? You have learned it. It will come 1 on the ortho position. So COCH3 at ortho, and plus number 2, it will come where? It will come at the para position. So here C double bond O CH3. So like this you will get the ortho and the para product. The para product is the major, and I'll just write the name of this product for you. This functional group, if you identify, is a ketone. C double bond is a O is a ketone, and certainly ketone has higher preference as compared to a halogen. So this is 1 and that's 4. This compound is called 4-chloro. It is called 4-chloroacetophenone. This is 4-chloroacetophenone. Benzene with a COCH3 group. Okay, benzene ring with a COCH3 attached to it is known as acetophenone. It's a common name of this ketone. And fourth position you have a Cl. So this is 4-chloroacetophenone. So these were the 5 electrophilic substitution reactions of benzene ring, namely halogenation, nitration, sulfonation, Friedel-Crafts alkylation and Friedel-Crafts acylation.